So they can see me and hear me. You're going to connect that. Okay, good morning. Can you see me and hear me? Hello? Yeah, okay. Okay. I am yet to see you guys, but it'll be ready. Hopefully, this delay will not happen every time. So this is a course on algorithm design and analysis, and it will be jointly taught by Aritra Banik at IIT Jodhpur and myself. You will see my email address. There is a website. So there is a course website already set up. It tells you the kind of material which we plan to teach and what we assume and what kind of background we expect. So typically this course takes off from the data structures and algorithms course you have seen in the previous semester, I guess. And so we will move on to advanced data structures, advanced algorithm design techniques, advanced algorithm paradigms, and so on. So this is an important core course. Typically, every computer scientist should know certain toolkits for algorithm design, and that's what this course will cover. Okay. So if you have seen the course website already, is Aritra there? Okay. So anyway, I think he will send a link to the course website. You've seen the course website. It tells you what material we will cover and what we will assume. So I would encourage you to go check those. Check, there is a reference book, and in particular on the background material which you are not familiar with, please check the reference books and refresh your background on those material. Okay. So I'm going to start today on amortized complexity of data structures. So you then know, since we are doing this remote, I would suggest if you cannot see or there is a breakdown, please, one of you should just come to the mic and convey, because I am going to assume that everything is fine unless I hear from you. Okay. Okay. So you've seen worst case complexity of algorithms and data structures. You have probably also seen average case analysis. For example, you probably know that quicksort, even though in the worst case may take in square time, it's on the average, for some meaning of average, that it takes n log n time. And what we are going to do is to see another measure of analyzing the running time. In particular, this is a lot more relevant for data structure problems, amortized complexity. Okay. So let's look at what is a typical data structure problem, right? So a typical data structure problem, you want to maintain something, some set of objects, and you're going to support some queries, right? These queries may change the data structure, some may not change the data structure. So typically this is a typical data structure problem, right? An array, a linked list, a stack, or a queue, or a heap, priority queue, dictionary. These are all typical data structure problems where the objective is that you want to maintain something in an efficient way so that these queries, whatever you are asked to support, can be done efficiently, right? So let's just look at something which you would have seen. Suppose I want to support membership. Okay, so if my query is just membership, right? I want to represent a set of some numbers. So I want to maintain a set of numbers, and the query is given an element X, is it in the set or not, right? So what would be a typical data structure? How would you do this, and how much time does it take to answer the membership? I guess you have to come to the mic and answer. So can somebody answer this? Like, suppose my data structure problem is maintain a set of numbers, and the query is that given an X, is it in the set or not? So how would you maintain it? Can you hear me? So somebody please answer. Yeah. A BST, okay. Something even simpler, because the only query I have told you is membership. Sorted array, right? So you keep your list in a sorted array. And how much time would it take to answer the membership query? Log n time, right? So you'll do binary search. Now this log n time is worst case, right? I want to just pay attention to this because I'm going to talk about amortized complexity. Okay. So somebody said BST. So what would you use BST for? So suppose I want to represent, I want to represent insert, search, and delete, right? All these queries. Then what kind of data structure would you use? A binary search tree. Any binary search tree would do. And what kind of a running time for this queries? I'm also going to use this opportunity to refresh something you should have learned. Okay, so this is, and before I get there. So if I want to support these queries, what data structure would I use? Just any binary search tree? So you need a balanced binary search tree. There are a lot of such beasts, red black trees, AVL trees, B trees, whatever you've learned. So you can do this in log n time. So if I care only about membership, I don't need any sophisticated structure. Simple array would do, a sorted array. But if I also want to dynamically change my data and insert and delete things, then you need what are called balanced binary search trees, right? Suppose I want to support only insert and delete max. What data structure would you use? Right? I'm not searching for an element. All I care is, think of it like a queue, new elements are getting inserted, and the maximum element, high priority element, is deleted. So what kind of a data structure would you use? A max heap, right? Why not this? Why not balanced binary search trees? Okay, so somebody said max heap. Again, you can do all of both of these operations in log n time, but why not balanced binary search trees? Can I use them and can I not, or why not? If I only care about supporting in logarithmic time.
You have to search for max now. If you are not using max heap, you have to search for max and priority element. So in that case, this query will be only of just delete and then do further change.
Okay, so the answer is that in a balanced binary search tree, if I want to delete max, I have to search for max. But how much time does it take to search for max? Log n time. So what's the problem? If I care only about log n time, you can search for max and then delete it.
Then you have to again rebalance.
Even here you have to rebalance it anyway, right? Even in max heap, the root will have the max, so you'll delete it and you have to do some rebalancing anyway, and that's what takes log n time.
But if I maintain such a structure, like whenever I insert, so I insert in the max heap position. In that case, we will not need to rebalance.
I don't know. Insert is an arbitrary insert, right? Somebody is coming and an adversary is giving you a value to insert. Okay, so this is a question I want you to think about. Okay, not a hard question, but this is the kind of question you should ask and answer at the end of a data structures course, right? Okay, so the one answer is that if I only want to find max, then this data structure is constant time because it is at the root, whereas here you have to spend it at log n time. But I did not tell you that as a query. My query set is insert and delete max. Okay, so if I just say find max, then yes, in a heap you can do it in constant time, whereas here it will be log n time. So think about it. Why do I need heap? Why not use everything using balanced binary search? Okay, this is a simple answer, and this is this kind of thing. You want to just sort of contrast data structures and get a feel for when do I apply this, when do I apply that kind of thing. But I'm going to move on and say that in all these cases, the time I'm saying is the worst case time. Okay, so that means for any operation, in the worst case, it takes this much time. Okay. Now, what is a typical application of a data structure? There are two kinds of applications. One is that the data structure problem may be the real problem, right? Like Google, you give a query and you want to get the answer, so you really care about worst case time. That I want to get the answer very fast, so it's important that I have a good worst case time, right? Maybe you're searching for a word in a dictionary, then you want to do search, you really want fast worst case time. But there are situations where you are applying these data structure for some other problem. Let's say, what would be an application of heap you would have seen for some graph problem? Do you recall in your data structures algorithms course, for some graph algorithm, you found useful to apply heap? Anybody remembers the problem? Yeah. For example, Prim's minimum spanning tree algorithm, or in Dijkstra's shortest path algorithm, typically heap is applied. So I'll just quickly or Prim's minimum spanning tree algorithm. Again, if you have forgotten them, you should just go refresh your memory on this. It turns out, okay, I'll just tell you how the algorithm works, right? In a Prim's algorithm, you have some, or let's say shortest path, Dijkstra's shortest path algorithm. You want to start from some vertex S, and you want to find the shortest path from S to every other vertex. It's a single source shortest path problem, right? At any point of time, you have some set, and these are the vertices for which you have found the shortest path. The remaining vertices are outside, and you pre-process and compute for every vertex some distance from S through vertices of S. That means for this vertex, you look at all paths from this source vertex through some vertex of S. So it will be like this, any of these paths. Among all this, you found the shortest path and you pre-process and store them. And then the Prim's algorithm or the Dijkstra's algorithm goes like this iteratively. I'll find the smallest among this, I'll delete them, put it inside, and now update these distances because a new vertex is gotten into S. Some distances change, update it, find the smallest among the d values, delete them, put it inside. So the algorithm will iteratively delete min of the d values, include it in X, in S, update d values, and it's a loop which keeps happening, right? So you have this distances computed, initially some pre-processing, and then you delete the smallest out of them, delete it, include it inside. After you include, because of this new vertex, some distances change, update those distances. So this vertex came in. So through this vertex maybe, so this vertex X came in here. In the next iteration through X, maybe some of these distances might become shorter, so you want to check and update that. And then among all these, you delete the smallest, keep updating it, and that keeps happening in this loop. Okay. So now, because it's a delete min and this updating d values is actually decrease key values, right? So this is, I would replace it as decrease some key values. And keeps happening, okay? It keeps happening some n times, okay? Now in this case, my goal is not necessarily the worst case running time for one of these operations. I don't care about one delete min taking long time, as long as the sequence of n operations take very fast, then I have a good running time for Dijkstra's shortest path, prim spanning tree. Okay? So the goal is not the worst case running time for one operation, but the goal is time for a sequence of operations. So amortized complexity is this notion of average time, but this average is not over some probabilistic randomized distribution or any such thing. Average time over a sequence of operations. I don't care about one time, one operation, minimize the total time. Okay, so and the motivation is that problems like applications of your data structure to some problem where iteratively you are doing a lot of these operations, then the emphasis, the goal I care about is not just the time for one operation, but the time for a sequence of operations. So it's the total time for a sequence of a large sequence, some t operations divided by t. Okay, so this is the amortized complexity of that operation. It's still worst case maximum over all sequences. Okay, we will see some examples where things will be very clear, but the point to note is the goal is not the time for one operations, but time I'm doing a lot of these operations. I mean, why would this be a better measure of the running time, and why? So obviously, so I care about total time for t operations. If the worst case time for one operation is some log n, then the time for t operations is t log n. But this may be an overestimate, because this worst case may not happen all the time, and that's what we are trying to capture here. Okay, some worst case may actually make the data structure nice, that subsequent operations may be faster. Okay, so it's like this. So my favorite example is, suppose I want to find out your average daily expense. Okay, because I care only about your total monthly expense, right? The total time for this sequence is more important for me than what is the maximum you spend on one single day. Okay, so I can say, let's say what is the maximum you spend on any single day? You paid your mess fees 2,000 rupees, So I'll multiply by 30 and say 30 into 2000, your monthly expense is at most 60,000, right? This is clearly a gross overestimate. This is like saying, oh, your worst case per operation is log n, so total time for t operations is at most t log n, and this could be an overestimate, right? Exactly in this case of your monthly expense, I ask you worst case, what is the maximum you spend on any single day, and you said 2,000 rupees. Then if I just say, oh, okay, so the maximum, your monthly expense is 30 into 2,000, 60,000. It's just a gross overestimate, because the reason you spend 2,000 on a single day is to amortize your food cost over the whole month, right? So it's actually, it doesn't happen all the time. That's the whole point. The worst case doesn't happen all the time. So somehow you want to capture this dependency in this sequence, that there is one costly operation, it actually makes subsequent operations cheap. I want to capture that somehow, and that's what makes the amortized complexity a little harder to actually do this estimation. Okay. So is it clear? Any questions? Then I'll just get on to giving some examples. So the challenge is to actually capture this dependency between these operations. So I am interested in a sequence of operations. So here is a worst case operation, somehow that makes a lot of other operations cheap. How do I capture that very carefully and then do this good, better estimate than simply saying T log n? And that's what is the challenge, right? That's what makes it harder. So let's do this example of incrementing a binary counter. B bit counter. Okay. So let's say I have a B bit counter which looks like this. So this is B bits. This is my data structure, just a simple B bit vector, and the query or the operation I want is just to increment. Okay. So how do you increment? What will be a code for increment? Let's say if the counter is x1, x2 up to xb, then here is a code, right? While xt is equal to 1, t is changed to t minus 1, and xt is changed to 0. And when you get out of it, xt would be 0, and I will change this to 1. So that is a simple code to increment, to see what's happening. So what am I saying? How do I increment this, right? I want to increment. I start from the right, change all the 1s to 0. Until I hit a 0, I change it to 1 and just leave it like that. And that's what's happening, right? I start from the last bit. If I see a 1, I change it to 0 and then move left. And when do I get out of the loop? When I see a 0, then I change that 0 to 1. So all that carries are changed, then the 0 is changed to 1, and that's the increment operation. Okay? All right? Now, what is the worst case for an increment operation? Yeah, so what is the worst case? B, right? Because you might just flip pretty much all the bits. So worst case is B, but I want to understand the amortized complexity of this increment operation. By that, what do I mean? That suppose I do a sequence of T operations, some large number of operations, maximize over a sequence of these T operations. divide by t, what is this average? Will it be, if I do t operation, is it really t times b is the question. Clearly, you don't expect this to take b bits all the time, but does it, maybe it takes b by 2 or b by 10 bits all the time. No, even that doesn't happen is what we want to argue. Okay. So, the question we want to address is what is, suppose I start from 0, 0, 0, 0, 0, 0 and do some t increments. And t is something smaller than 2 power b, let's say. So, that means I don't get into all ones and then going over, I need one more bit, I don't get into that. If I do t increments, to what is my total time? That's the claim. That's what I want to understand, estimate, and something like this. So total time, so starting from 0, 0, 0, 0, 0, 0, 0 b bits, total time for t which is much less than 2 power b increments. So how do I estimate it, right? Again, it's very easy to say the worst case is b, so totally at most t times b. But I want something tighter, little better estimate, and why do we think it is much less? Because it's it cannot happen b all the time. In particular, see that if suppose one operation takes a long time, right? That means it creates a lot of zeros. And zeros are good, right? Because the subsequent flip would be just cheap. And somehow we want to capture this in our total computation. And because of this dependencies between these operations, it's a little harder to carefully count this. So how do I count this? Okay. So in Karman's book, he mentions 3 different ways of doing this analysis. And one is this aggregate analysis. Right. So let's actually do this calculation. So first increment, how many flips, how much time will it take? 1, right? 1 bit from flipping. The next increment, I'll change this to 0 and then it'll be, cost will be 2. And then 1 again, right? So as you can see that it's going to be like 1, cost will be 1 every other time. So here how much time now? I change this 1 to 0, this 1 to 0, this next 0 to 1, so it will be 3. Next time it will be 1. And next time it will be 1, 1, 0, so the cost will be 2. So somehow, I'm interested that I want to count this number, totally how much it is when I do this t operation. And I can actually hard code it, compute it carefully and add them all, but we want to see is there a cleaner way of doing this estimate, right? So let's do this sort of column by column. Let's ask this question, how many increments so number of increments out of my t increments that will flip the last bit. How many increments will flip the last bit? Yeah? How many of my increments will flip the last bit? None of them.
Increments, the number of increments we are doing is less than 2 per week.
Yeah. Last bit meaning this last bit. This is the last bit. Sorry, yeah, this is the last.
Then it half exactly to power b minus 4. I mean, next time if you change it 0 to 1, in the next operation you have to again turn it. Alternatively, it's getting changed.
Yeah, but I'm talking about flip. That means both change is a flip. Whether I change it to 0 to 1 or change 1 to 0, I'm calling it a flip.
Oh, okay. Then it will be the
T times, right? Every increment flips it. Every increment flips it. So it will be T. Okay. So what I'm doing is, what is my goal? That I know first increment takes this much time, second increment takes this much time, third increment and so on, and I want to count them all totally, right? I am trying to do this count in a slightly different way. I'll say, okay, how many, what is the time? The time is basically the flip, number of bit flips, right? So, how many of the increments will flip the last bit? All of them, so that is T. How many of them will flip this next last bit? T by 2, right? The second last will be T by 2, right? Because half of them will just change the 0 to 1 and stop. So it is the other half which will come to this bit and change it also, T by 2. How many will change this flip? This bit? You will see that it will be T by 4, right? Because only, it will be like 0, 0, 0, 1, 1, 0, 1, 1. Until that point, this bit will be not touched at all. After that, it will be flipped, right? So the third last bit will be T by 4. So my total time, which is the total number of flips, will be T plus T by 2 plus T by 4 plus T by 8 plus up to the point of my T bits. And what does it sum up to totally? 2T, right? It's a geometric series, T by 2. So total time, so total number of flips is 2T. Even if I go all the way up to infinity, which I won't, because they're only doing totally T number of flips. But even if I go all the way up to infinity, T plus T by 2 plus T by 4 plus T by 8 will add up to at most 2T. So what we have seen is that even though the worst case is B, the amortized cost is the average over any sequence, so it's 2. So the total time for a sequence of T operations is not T times B, but it is actually T times 2. So the average, the amortized cost of an increment is 2. Okay? So it's a much better estimate than simply saying T times B. Okay? So amortized cost of an increment is at most 2. Now, this is it. This is all I want to understand. I know I'm doing a sequence of T increments. What is the total time? So this is called an aggregate analysis, because somehow we can look at the overall set of increments and take a holistic view of the whole thing and do a careful analysis, which may not always be possible when we actually get to complicated data structures. Okay. So there is another aggregate analysis or method. There is another method which is called credit or accounting method. So all that's happening is that some operations are expensive, some are cheap. Somehow we want to balance the cost and talk about the average expense, right? Average cost. So one way to do this accounting is that Again, let's just go back to finding out what is your average expense, right? So I give you maybe 80 rupees every day. So some days you spend 50, some days you spend 40, some days you spend 200, whatever, it keeps going. So whenever you spend less than what I give you, you put the remaining in your bank account, and whenever you need more, you will take it from your bank account. Okay, so this is some sort of a credit, and my average cost will be based on, how much do I give you so that you never have to borrow. Okay, so whenever you spend less than what you are given, you put the remaining in the data structure, and whenever you need more, take it from the data structure, and you never have to, somehow the amount I'm going to give you, that is amortized complexity, amortized charge, right? The average cost per day is enough so that whenever there is an expensive operation, there is already enough in the data structure. So if I can come up with that kind of an amount, that is the amortized complexity, because it's just the average cost, right? So this idea of putting the extra in the data structure is this credit method. Where do I put it, how do I put it, and how do I come up with this credit charge per operation is again the more interesting, challenging task. So let's say I give each increment operation comes with a charge of 2 units, whatever our measure of cost is. So I'm going to say, so each increment operation I'm going to give 2 unit, and if I can satisfy this condition that whenever you need more, there is always something in the data structure. If I can manage to satisfy that and argue that that's possible, then the average cost is 2, right? So initially, so in the first operation, it's actually using only 1. So the extra 1 will be put in the data structure. So there is an extra 1 in the data structure. This comes with 2 and it uses the 2. So there is an extra 1 still there. And then there is an extra 1 accumulated here because of this uses only 1. So there are 2 units of the data charge in the data structure, but this requires 3, so this requires an extra 1. It will take it from here, and still there is 1 there. So if I say that if I give everybody 2 units, everybody will pay for it either with the charge it's coming with or from the data structure, then the average cost is 2. So amortized complexity of this thing would be 2. Okay, but how do I prove it? How do I prove that if there is an expensive operation that comes, that it will have enough in the data structure to pay for it, right? How do I prove that? It turns out there is a very simple argument here. Let's look at this code. Every increment operation changes some 1s to 0 and some 0 to 1. Okay, how many 0 1 flip it does? How many 0 1 flip any increment operation does? Exactly 1, right? There is no variation. It's exactly 1, right? Once it changes, lot of 1s may get changed, but when it changes a 0 to 1, it happens exactly once, and that's happening here. Okay, so now here is my charging argument, right? Every increment operation comes with 2 units. 1 unit, okay, so what you do is, if you change your 0 to 1, pay for it from your charge, okay, and keep an extra charge on the 1. That's it. I give you 2 units of charge, and the way you should pay for it is that whenever you change a 0 to 1, charge it to this 1 rupee, and put the extra 1 on the 1 you created. Now you should ask, okay, I'm changing all the 1s to 0s, how do I pay for it? How do I pay? I think we lost. Yes, sir. Last site. What time is it? 1. we have another 15. So pay 1 unit for 0-1 flip and put 1 unit of charge on the newly created one. Okay. So I am going to give an increment operation 2 units. Here is 2 rupees. Whenever you change a 0 to 1, use 1 rupee, and you create a new one, put 1 rupee on that. Yeah. Yeah, I did not say much. Yeah, I'm just saying. So what I'm saying is each increment operation, I am going to give a charge of 2 units, 2 rupees, let's say. Okay. And I want to argue that that's enough. That's enough that if somebody uses less than 2 rupees, they'll put the remaining on the data structure. If somebody needs more, there is enough in the data structure to use it. That's what I want to argue, so that then the amortized cost would be 2. Okay. So we already, we finished with this analysis saying the total time is at most 2 times t. I want to give another way to do the same argument. So here is my way of using the 2 units. When you create a 1, you create exactly 1 1. Remember, there is exactly 1 0 1 flip happens. Pay 1 unit for that 0 1 flip and